Welcome to my masterclass in dimensional modeling. My name is Nick Galemo. In this session, we look at what is dimensional modeling, why it exists, and what it is trying to accomplish. Bill Inmon developed the concept of data warehousing. Dr. Kimball showed how to make it work. The dimensional approach allows for rapid data loads and direct control over dissemination of information to analysts. It also provides the simplest means to access and query data. In a dimensional data warehouse, data is ready for immediate use. All other methods have both a primary data store and a secondary data store for actual analyst use. The requirement to move data from the primary data store to the secondary data store introduces delays and additional complications to present the data to users.
In the beginning, there was the sequential file. This could be a card deck or magnetic media such as tape or disc or a drum. Prior to relational databases, systems ran using index sequential files. These were files that provided an index on the primary key, allowing random access to the data. The system gave you no help. You had to enforce your own transaction control. Because of this, application systems were generally simple, part because of complexity and part because hardware was not that powerful. Transactions were limited to single actions at a time. For example, you go into an airport and want to change your flight. After the clerk takes your ticket, they look up the flight that you want to take to see if seats are available. If there's room, the clerk will release your current seat. That is necessary as the system prevents assigning a new seat to someone who has one. This is to prevent the clerk from forgetting to release the seat after ticketing. The clerk will then attempt to place you on the new flight. Sometimes they find the seat taken. This is common when flights are delayed or canceled, and then they need to look for another seat. At that moment in time, you have no idea if you're going to get out of the airport anytime soon. The clerks were manually performing transaction control. Sometimes it works, sometimes there are two tickets for the same seat. Then in the 1960s, Codd and Date got together and defined relational theory. This led to the concept of relational databases. This was the great leap forward. Fundamentally, the concept was very simple. Yet it wasn't until over 20 years later, the release of Oracle, that relational databases came into being. In a relational database, the fundamental unit is the table, also known as a data set. A table contains rows and columns. Each row has the same columns. A row has a primary key and must be unique to each row. More importantly, the database provided transaction control. To gain acceptance, Edgar Codd developed a proof that if your model achieves third normal form, you are guaranteed data will not become corrupted. This created industry acceptance of the concept, and it moved forward. Normalization is a methodology used to define operational databases. Here is an operational schema for a sales system. Such databases are capable of supporting any number of active transactions without messing up the data. There are 5 levels of normalization. When your model is in third normal form, as is this one, every data element exists in one and only one place. This is great for processing transactions, but difficult for reporting. Producing a report was a challenge. It requires explicit design documents, planning, budget, and usually 3 or 4 weeks coding and testing in either COBOL or RPG. We needed a better way. It started with the release of the Data Warehouse Toolkit in 1996. In it, Dr. Kimball explains his method for designing relational databases solely for the purpose of data analysis. He based his design on the basic principles of any form of numerical comparison. If you want to compare two numbers, they must be in the same context. So, dimensional modeling breaks data down into two categories: measures and context. Measures provide the how much, the magnitude of the event. Context provides the who, what, where, when, and why part of the event. These are carried in the database with measures stored in a fact table, and context is stored in dimension tables. He introduced the star schema as shown here. This represents the same sales information as the previous model. Fact table in the center, surrounded by dimension tables. Every fact row contains measures and foreign keys to each dimension table. When you query a star schema, every measure in the fact table is surrounded by many dimensions with many attributes, all readily available to compose a query. When you query a star schema, every measure in the fact table is surrounded by many dimensions with many attributes, all readily available to compose a query. Now, with a large variety of front-end query tools, everyone can do their own report whenever they want. And since the star schema exposes all context, users are free to create any report that is supported by the grain and dimensionality of the report. Grain? In whiskey and dimensional modeling, grain is important. While whiskey mixes grains, it is not recommended in dimensional modeling. So what is grain? Grain is a statement in business terms that defines the content of a single row in a fact table. For example, if you are designing a sales fact table, the grain would typically be 1 row per order line. A fact table has one grain statement. Never mix grains in a fact table. Create another fact table at that grain. For example, I was building an order-to-cash database encompassing sales, fulfillment, and invoicing. Their operation worked at the order line level. So, with 3 facts at the same grain, it was simple to consolidate the information into a comprehensive view of the business from order to cash. However, there was an additional feed providing information on how the price was calculated. The grain was price codes on an order line. This went into another fact table that will be used by marketing to analyze the effect of promotion deals and the effect of less than truckload orders on cost. The grain statement provides clarity to the analyst as it fully defines the content of the table. I mentioned dimensionality. This is the number of dimensions to a fact table. It has nothing to do with grain. It is simply an expression of how much data is available. In conclusion, dimensional modeling is a physical relational database modeling method exclusively for the purpose of performing analytics. It differs from normalization in that the focus is the ability to store massive amounts of data efficiently in a relational database for analytics. SQL was developed for relational databases. However, with the advent of Hadoop and the cloud, many non-relational databases adopted SQL as the means to query data. For example, databases such as Couchbase and CosmoDB have a strong SQL implementation. These are document databases and are not suitable for dimensional modeling. Technically, they could, but performance would be abysmal.
As you can see, the star schema provides the simplest and most efficient way to provide comprehensive data analysis capabilities. Relational databases created the environment that led to an explosion in online interactive systems. Dr. Kimball showed how they can be leveraged to provide rapid and efficient data analysis through the star schema. In future sessions, we will look at the various database systems today and issues with modern architectures and how to optimize them to improve the user experience. That is why I created this Patreon site, to address dimensional modeling itself as well as its application to alternative data structures. As a member, you can participate in discussions, ask questions, and influence others. Even suggest topics. Please. Your support will help me build a complete library of dimensional modeling principles and implementation tips I have learned over the past 25 years. Also, we may uncover new methodologies when dealing with non-relational sources. We will never find out unless we try. So join me. Become a member.